Hello, everyone. Welcome back to another episode of Tantra's Mantra, where we go behind and beyond the tech news headlines. I am Prakash Sangam, your host and founder of Tantra Analyst. As we all know, 5G has seen unprecedented growth in terms of operator launches, device launches, subscribers, and so on. Now, everybody is asking what's next. Just to level set, what is commercialized today is 3GPP release 15 version of 5G. This was the first release that supports 5G for sure. Release 16 specifications were finalized by 3GPP in June of last year. Release 17 is expected to be finalized early next year, and the work on release 18 has already started. 3GPP held a highly attended workshop on release 18 in July of this year, with lots of contributions coming. So the answer to the question, what's next for 5G, is quite a lot. There was also some respite to enthusiastic marketing folks who were ready to jump the gun and start discussing 6G as a next step to 5G. 3GPP approved 5G Advanced as the name for the next phase of 5G. 5G Advanced will start from release 18 and may run for a couple of releases, which is typical in 3GPP. Any discussion of 6G will come after that. Quick shameless plug here. I have an ongoing series of articles on evolution of 5G that you may want to check for more details. I have included a link to the article series in the description of this podcast. Please do check it out. Today, we will take a deeper dive into 5G Advanced, especially some of the new and exciting concepts it is bringing to the table. And to do that, we are delighted to have Dr. Tingfang Ji, Senior Director at Qualcomm, working on flagship 5G research with us today. Tingfang, welcome to the show.
Thank you, Prakash.
Yeah, thank you for coming over. Let's start with some quick introduction. Tingfang, I see that you are a long-time Qualcommer. Could you please briefly explain your background, what you do at Qualcomm, and most importantly, your work on developing new radio technologies and standardizing them through 3GPP?
I've been with Qualcomm for more than 18 years. When I first joined, actually, that was about the time of transition between 3G and 4G. So we started working on some of the OFDM type of modulation, OFDMA type of medium access. So yeah, that was pretty exciting. And I worked in 3GPP, the standards body for LTE and now 5G. And I also led the radio group discussion for a few years. And 2014, starting from then, I start lead the system design for 5G. And now I have a interesting and a very broad topic to study in my project is, like you said, what's the next phase of 5G and, even forward looking, what's 6G. So this is a super exciting opportunity for myself and for Qualcomm to further develop wireless technology.
Very well. Tingfang, being a 3GPP member, I know that you worked on some of the most fundamental technologies, some might call building blocks of 5G. And these make 5G very flexible and very forward looking, which is a little bit different than the previous generations. Could you explain some of them?
Yeah, we had a really bold vision when we first started discussing 5G. So, of course, Qualcomm is driving it, but we also have many partners, the info vendors, OEMs, and operators. We sat together for a few years to talk about what to enable in 5G. One of the biggest vision is that 5G should not only be for smartphones. 5G should be natively designed to support other devices. You can in general call it Internet of Things, right? It can be a massive IoT, or we call it a critical IoT. So the massive IoT are these large scale smart sensors, actuators, those type of devices. You can have billions and billions of them, or the critical IoT, which require really low latency and high reliability. So those are the type of things we wanted to design for. So to make it happen, we had a few critical technology inside 5G. One is something we call scalable numerology. which means that the same design can be scaled up and down very gracefully. So instead of LTE, for very technical readers, you will know that there's something called carrier aggregation. You can sort of linearly increase the capability of a device. And in 5G, what we can do is exponentially scale the design. So you can cover either an even bigger range of devices. And also, of course, we introduced millimeter wave. We introduced the LDPC channel code, which is super powerful for high-end devices. And we have a flexible multiplexing structure. So an operator can actually offer all type of services over the same spectrum, using the same asset that they have. So those are sort of the biggest building blocks for 5G.
Cool. So I hear that you have more than 1,000 patents related to all these cellular technologies.
Yeah, it's not my patent per se. Right? This is really teamwork. So we have a very talented team, and these are the inventions that we have on 5G, and some of the big ones that we talk about, like scalable numerology and flexible frame structure coding. So those are some of the flagship patents that we have. Very proud of it. I think we'll have more opportunity to invent more, given we're at the cutting edge of wireless technology.
Very well. So, folks, another important aspect of patents is this conundrum between quality versus quantity. There's a lot of discussion on it. I have a lot of views on it, which I've expressed through my articles as well as podcasts and so on, in terms of discussing with other experts and other things. I'll include links to those discussions in the description, so please do check them out. Okay, so going back to the 3GPP releases and so on, I think release 16, 17, and now 18 are setting up very nicely this next phase of 5G, looking at verticals, not just smartphones and broadband, right? That's an exciting area of innovation for the whole industry as such. Now let's quickly jump to 5G Advanced, which, as I mentioned, will start from release 18. I have some specific questions on release 18 as such, but what areas you think release 18 specifically and 5G Advanced generally will focus on?
That's a very good question. Actually, we don't know exactly what will be in release 18 or 5G Advanced yet. In the previous three releases, release 15 laid the foundation of 5G. Release 16 and 17, we really expanded 5G to the verticals. According to the vision that we had, we introduced V2X, which is car to car or car to infrastructure communications, which can also be used for public safety disaster scenarios. And then we also introduced this thing called the UR-LLC, which is ultra low latency and high reliability communications. So those are for like industrial sensors. We introduced a couple releases on positioning technology. So this is something that I think is super promising. Now you can actually, just like you have GPS or GNSS for location outdoor, with 5G, essentially you can do this similar accuracy or even better, not limited to clear sky, but in urban canyon, inside your home, in your factory. So those positioning technology, it has also been advanced. So 15, 16, 17, those three releases are really blockbusters. We have tons of feature packed in there. The next release we called 5G Advanced. This is sort of a reset. We're thinking of, can we now introduce something more fundamental to study and potentially to bring some completely new element into 5G? So there is artificial intelligence and ML. It has been making a big impact elsewhere. We're thinking whether it can, what we can do in 5G to take advantage of it. And we'll also have, XR. This is AR, VR, this type of new user interface. How do you deliver this type of service over the next generation of 5G? And they're full duplex, and they're network energy saving. There are these zero power wake up radios. So we have a few, in some sense, brand new technology we want to introduce in 5G Advanced. So that's ambition, and we'll study it and eventually how much of these have enough traction that's worthwhile to standardize, we'll know after releasing studies.
Very well. That kind of nicely set up my next set of questions. As you rightly pointed out, there are these four areas that you mentioned: artificial intelligence, XR, AR, VR, full and half duplex operation, and network energy savings. I leave the XR AR for a later part for two reasons. One, it is a large area on its own, and there's tons of stuff that's already been talked about, and so on. So we'll discuss that later, but we'll focus on the other three you mentioned, which are very interesting and new, at least in my view, in cellular standards: AI and ML, duplex operations, and energy saving. So let's start with the first one: artificial intelligence and machine learning. It's generally known wireless is a very complex topic, and using AI and ML for solving wireless challenges is a given. I'm surprised it took this long for it to be really a focus area, right? So, what are some of the AI and ML aspects that you're looking to standardize?
Yeah, like you mentioned, OEML has been around for a while, and it has a huge impact in terms of computer vision, compression, even audio processing. When you talk to Alexa, those are AI/ML.
Yeah.
We have already been actually using AI/ML in wireless comm for a while. Some of the info vendors and operators have been using AI/ML to optimize the network operation. And Qualcomm, we had already had a couple generation of AI and ML enhanced modems.
Uh-huh.
So there we have algorithms fine tuned with the machine learning algorithms. Actually, it's really amazing how much they can do. In standards, we have another question: is you can use AI and ML to do optimization based on the data that you currently have, and you have proprietary implementation. The question is, if I have a AI ML on the modem, and I also have these neural networks on the network side,
Uh-huh.
each of us try to guess what the other side is doing. For a problem that requires end-to-end solution, you might be having two AI fighting each other. You might be undoing each other's work, right?
Yeah, correct. Yeah.
What we're trying to do in standards is to see, first we want to evaluate how big an impact AI/ML has for some of the fundamental areas, physical layer, medium access, resource management, mobility. So first we want to evaluate how big is the impact.
Yeah.
And then we want to see how you can make these nodes work with each other. Can we coordinate between them? Can we actually allow the network to manage the different models, the neural network models,
Uh-huh.
on the network and the UE side in an efficient way? And can we manage the data? Because you need training. So you will need reinforced learning, most likely. And you want the dynamic update
Uh-huh.
of these models on the device. You might even want the federative learning, to actually reduce the amount of data that need to be shipped into the cloud. So it's a really big topic. And I would say the biggest one, the ultimate solution would be to actually have the area interface itself,
Uh-huh.
instead of explicitly specified. Can you actually simply define some of the components as talking to each other as a pair of neural networks and leave the area interface dynamic?
Uh-huh.
Because we know how fast a neural network advances, right? In weeks and months, you can see neural network have different performance. Is it possible to make the area interface dynamic?
Uh-huh.
And we can actually ride on the fast pace of neural network advancement instead of relying on every release, every couple of years, you have an update of the technology. Can AI/ML enable a new mode to allow the technology to advance at the pace of a neural network advancement itself? So that's an even bigger topic. We call it the dynamic area interface based on AI/ML or cross-node machine learning. So something that we're looking into. It's a super exciting topic.
That's fascinating. So you basically, just to paraphrase, you'll kind of put some guide bars, if you will, and then let the transmitter and receiver decide how to best utilize the radio link using AI and ML, you're saying?
Yes. That's in the in bigger picture, that's what we're thinking that it potentially could happen. Of course, you still need to solve all the interoperation testing issues. But that's in the details. So yeah, so this dynamic air interface across node machine learning is a big concept that we're evaluating, we're studying.
That's very interesting. So, when it comes to AI and ML, so far most of the work has been all proprietary, right? Not just cellular, but even otherwise. Standardizing something of that sort, and especially, companies kind of have differentiation based on their AI ML algorithms. So, how does this standardization might work without companies giving their secret sauce away and differentiation away, right?
That's a great question, right? So that's pretty much in line with what I was thinking. Ultimately, you want the network to actually evolve,
Uh-huh.
right? You don't standardize something. You leave the flexibility for someone to implement their neural network, with differentiation. But at the same time, standards can make sure these models work together. So standardization is more about coordination of these models, and maybe you can have a proprietary implementation, but it can be managed by the operators or device vendors. Say Qualcomm, we have a neural network that can work really well in the network. If the network is in particular mode, then I can update these models based on the network assistance, based on the deployment scenarios. I can still maintain my differentiation. Or even better, say, Ericsson, Qualcomm, we have something that's the same network with split cross-air interface. There's something called autoencoder for compression, for example.
Uh-huh.
Just take that example for, because it has been used in image video compression, it's very, very well known. So you have encoder and decoder on two sides, and but these autoencoders can be updated, and as long as we have tested it, we could actually simultaneously update the encoder and decoder and get a better system without any standard change. Standard just make sure that the interoperation of these nodes, these neural networks, are done in a cooperative way, don't break each other.
Yeah, the whole effort is a very tall order, right? So it'll be interesting and fascinating to see how it unfolds. And I think you answered this question a little bit as well. The intelligence, if you will reside across the network, right? It'll be on the cloud, on the network, on the devices as well, and of course on the edge cloud as well, with edge becoming really prominent in the future.
Yeah, that's a great point. This intelligent edge is something that is in the core
Uh-huh.
of Qualcomm's vision. So, because latency is something that's naturally associated with a deep cloud-based solution. So pulling the cloud to the edge and implement the machine learning on the edge of the network, it will give you much better performance compared to have everything sitting in the cloud. At the same time, we have also devices that are super intelligent. Our Snapdragons these days, I don't remember how many releases it is already before we had this, really powerful, machine learning chipset inside our Snapdragon. So when the network on the edge of the network, the neural network and the neural network inside the device collaborate. These will bring us the best possible performance. For this
Mhm.
power
Mhm.
hungry neural network that requires data that's sitting already on the device, you should actually implement the neural network on the device itself. For some of the other operations that maybe requires more horsepower and require aggregation of information, then you want to implement it, on the intelligent edge. So working together, this will be the ideal solution from overall technology perspective.
Very nice. And I'm sure there'll be a lot of talk on how this can be and will be standardized and so on. So, in the interest of time, let's move on to the second point we talked about, this duplex operation. Could you quickly explain what is half and full duplex operation?
Oh yeah, duplex is we call it basically when you have a transmitter and you have a receiver in a radio,
Hmm.
and when the transmitter and receiver work simultaneously, is called full duplex. And when the transmitter and the receiver take in turn to operate, is called half duplex. Typically in cellular spectrum, you manage it, we call it pair spectrum or unpaired spectrum. In the pair spectrum, you have a pair of spectrum where one is for transmitter, one is for receiver. They're far apart. Typically, it can operate simultaneously. You don't have much self-interference. And for unpaired spectrum, you have just one chunk of spectrum. And in those places, we call it the TDD, time domain duplex. In that case, it's half duplex. You either transmit or receive. The definition of full duplex and half duplex.
Correct. So full duplex is basically you're using the same chunk of spectrum for both transmission and reception at the same time, right? Which means, I mean, potentially it can kind of double the capacity of any network instantly without any additional spectrum or additional infrastructure, so to speak, right? Almost a holy grail for everything that is wireless, isn't it?
That's that's a holy grail. And I think what you said is the more generic definition. Precisely that full duplex is what it is. But there are also other variations of full duplex. Like we said, for FDD spectrum, say, you're at 1 or 2 gigahertz band, they're also full duplex. They're not using the same spectrum. So full duplex can also include that, you're not necessarily being on the same spectrum. As long as TX and RX are simultaneously enabled, we also call it full duplex. In 3GPP, the Release 18 study, actually, there are majority of people are thinking of technology called subband full duplex.
Correct.
Which is what means is you could take one chunk of spectrum and divide them into subbands. And on some subband you're transmitting, some band you're receiving.
Okay.
It's almost look like FDD, but you don't have guard in between. So you use a radio and digital technology mitigate interference between the transmitter and receiver.
I see.
So that's also a very powerful technology that allow you to basically reduce the latency, increase the coverage. There are many benefits comes with this full duplex type of technology.
So, I mean, key is interference cancellation, right? So, for this to really make it work?
Yes. Interference cancellation, or in general, you say interference mitigation, because cancellation typically refers to receiver side, right?
Yeah.
So the transmitter side, you can also mitigate the interference. There are many really cool techniques that you can use to reduce the interference from the transmitter to the receiver.
Quickly, can you explain some of them?
Oh, sure. So one of these is we call it the spatial duplexer, because typically duplexer is what you use in the in FDD spectrum. In those radios, you have a duplexer that allow you to do this simultaneous operation. It's basically a filter in frequency. But if you can do it in the space, there you don't have any guard in frequency to filter them. But spatially, if you can separate them. If you have something called EM blocker, you can put in between the transmitter and receiver panel. Then those type of technique, this is really RF and radio technique, can bring down the interference from what we have tested, like 80 dB or so. So that's really a fundamental technology. So that's just one example of not interference cancellation. This is actually a pure RF technique that can be used to reduce interference.
The technique as such has been known for some time. So what is making it come right now, not before?
Before, people were looking at the full duplex, where you said is TX-RX on the same spectrum. And you are using both RF and digital cancellators to remove the interference. But the limitation people observed is that they can only be used for small cell setup.
I see.
So what you have is if you can go to 1 watt transmitter with a couple of antennas, that's already really amazing. That's you're almost reaching the limit, because typically people are talking about cancellation of more than 100 dB, combining both digital and analog, and the suppression. 100 dB is
Yeah.
what that means is you have 10 zeros.
Yeah.
After this digit, you need to cancel out 99.9999999%
Uh-huh.
of the inferiors. It's really, really hard.
Correct.
So when the transmit power get too high, it's simply not feasible.
Uh-huh.
What's new right now? First of all, the big concept of sub-band full duplex that people are latching on right now is that I actually don't need to have them be on the exact same frequency.
Uh-huh.
If we can put them on adjacent frequency, this already covers many use cases
Uh-huh.
and can improve performance a lot. And just by pulling apart the spectrum, you have 45 dB oscillation.
Uh-huh.
So immediately, just think you have 1 watt to start with a full-blown cancellation.
Uh-huh.
Now all of a sudden you have 45 dB, additional isolation
I see.
because of the sub-band approach. Then full duplex now can be applied to the macro cells. It's no longer a small cell technology.
Uh-huh.
Now actually you can use it in the coverage frequency. You can cover kilometers of cell distance.
Okay.
So that's one big differentiation from the previous full duplex technology. Also, because digital cancellation, now we have more capability compared to 10 years ago when full duplex was invented. We can even cancel the 64 transmitters, 64 receivers, those type of cancellation. Of course, complexity is high, but as silicon advances, the process node keep reducing.
Correct.
We have just more and more horsepower to process it. So this is blowing new life into the full duplex technology, and hopefully we can see commercialization soon.
Yeah, I mean, complexity is our friend, right? As engineers, so I think the more complex, the better it is.
Yes, yeah, that's our tool. Yeah.
Okay. All right. So any numbers as such? I mean, how much improvement in terms of performance you're expecting with sub and duplexing?
Oh, yeah, we had actually a demo
Uh-huh.
on the full duplex system.
Uh-huh.
What we were showing in that particular setup was that we can see the latency being reduced by almost half, because for half duplex, the transmitter and receiver need to take turn waiting for each other.
Correct.
So with full duplex, you don't have to wait for each other anymore.
Yeah.
Actually, you could instantaneously, do a transmission and receiving, right?
Uh-huh.
So there is a big latency reduction.
Yeah.
And also we see the coverage enhancement, because sometimes the cell phone is power limited. So the range, the data you can get, it's really not about the bandwidth, but about how much power you can pump into the system. So half duplex, essentially reduce the power by a lot.
Correct.
Typically for TDD system, you will have like 3/4 of the time it's receiving and 1/4 transmitting. That means you lost the rate by a factor of 4.
Correct.
So now with sub-band full duplex, you can have a 4 times the coverage.
Yeah.
So those are the big numbers that we're talking about. Of course, those are simulations right now, and we have the hardware ready.
Yep.
And early next year, you'll see a live full duplex system from Qualcomm. We're going to demonstrate it to the whole industry.
Cool. That will be really cool to look at. And let's move quickly to the third area that we mentioned in terms of network energy savings. Obviously, energy saving is a big topic because of climate change and so on. And we can go on and on for hours talking just about that. So at a high level, what are some specific topics and areas that 3GPP is looking at reduce the energy consumption and improve energy savings?
Yeah, so actually, even at the beginning of 5G, around 2016, when we were actually defining what should the 5G be in 3GPP, we already said that energy saving, network energy saving is one of the big design goals.
That's cool.
If you look at current 5G system, there is so much reduction in the overhead channels.
Yeah.
It's already much greener compared to LTE. So it's already really a system that's quite optimized for energy saving.
I see.
So what we're thinking release 18 is some bigger, more fundamental design changes. So I would say that one of the unique aspect of this energy saving is that base station, when it's active, when it's transmitting, the power amplifier that's pumping up, this very high downlink signal, very high power signal, it's consuming bulk of the power,
Mhm.
from for the whole base station. So what we could do is that we can probably introduce more advanced RF technology
Yeah, of course. Yeah.
for those high power transmitters
Hmm.
to actually achieve better spectral efficiency. So for the same transmit power, I could actually support a much higher data rate if we introduce something called DPOD. Or this is a technology where the transmitter and receiver collaborate with each other, and with advanced processing, again, complexity. If we throw complexity at the problem,
Hmm.
actually the transmitter can be allowed
Uh-huh.
to operate at higher efficiency. So the power amplifier I talked about, currently 40% efficiency is already very good, right? And you might have even lower efficiency if you want the really high fidelity of the signal. Otherwise, it will be distorted. So
Okay.
what we're thinking is, can we bring that efficiency, up a whole level? Allow it to, the
Right.
DC power and radiated power make it get even closer. So while you're distorting the signal, when you're getting closer and closer to saturation, this is getting very technical. But the receiver, if you have some side information,
Correct.
maybe I can clean it up
Yeah.
and I can still achieve very high efficiency. So for the same data rate, you can either reduce the transmit power, or for the same transmit power, you can significantly increasing the data rate.
I see.
So because for the same offered load, offered traffic, that means you only need to operate in this mode less time, right? So you can actually shut it down more often. So there are some fundamental RF technology that we are looking into, and potentially that can bring a big change. Um,
Oh, I see. So, just to paraphrase, basically, instead of the transmitter working in its linear range where efficiency may not be high, pushing the transmitter to go into a non-linear but higher power output operating point, so you can transmit more, but any distortion can be removed with more processing, right? You're saying.
yes, that's what I'm saying. Is with advanced receiver processing,
I
the
see.
transmitter can be more power efficient. So
I
instead of
see.
say 35%, maybe you can achieve 55%.
I see. And you can use, AI to do that distortion correction in a better way as well, right?
That's certainly in our toolbox. Is something that we're looking into.
Okay. That's interesting. So, does that mean the transmitters have to be changed, or this can only be on new installations, or these techniques can work on the existing transmitters as well?
It can work on existing transmitters as well.
Okay, that's cool.
Yeah. So you basically need to enable the receiver to do the cleanup.
I see. Then you can see instant increase in efficiency without changing over all the hardware and so on.
Yes. So that's our ambition, and yeah, we'll have some demonstration as well for this technology coming very soon.
That's fascinating. I think we can go on talking for hours on all of these things. I wanted this to be more of an overview for 5G Advanced, and I'm sure we'll talk quite a lot as the standardization progresses and things are developed from 5G Advanced point of view as well as release 18. Any final comments on 5G Advanced before we close the podcast?
Sure. I think it's a really 5G advanced. You can consider it just the second phase of 5G.
Uh huh.
You guys are probably tired of watching all the 5G commercials on TV. Wait for the next round of commercial on 5G advanced. This because there are so many big game changers in 5G advanced. There's so much energy in making 5G even better. So not only the engineers should be excited about this, but I think your audience, they will also see 5G advanced coming, in a couple of years. There will be so many exciting stories to tell.
Indeed, a lot of things in the future, and not so far in the very near future as well. So, and I would love to have you back on the show to discuss all of those as well.
Great. Thank you, Prakash.
Excellent. Once again, thank you very much, Ting Fang, for coming over and sharing your views. So, folks, that's all we have for now. Hope you found this discussion informative and useful. If you did, please hit that subscribe button down there on whatever platform you are listening this on. Again, I'll be back soon with another interesting topic in another episode, putting light on another interesting subject. Bye bye for now.